Okay, so last time we looked at the isothermal transformation diagram, or we looked at how the isothermal transformation diagram was devised, and we um, examined the various phases that occurred when you rapidly quench a system and then you hold that system at a particular temperature. For example, we looked at austenite, which is really just gamma iron. And we said, well, if you rapidly cool austenite and let's say you hold it at 600 degrees, so you hold it for a period of time. On the isothermal transformation diagram, that's going to be the rapid cooling will be a quick drop in temperature and then holding. So we'll have a horizontal line to represent the time that we've held this material at this temperature. And as you can see, we have time on the x-axis. Let's move that down a bit. You can see times on the x-axis here. That's time. And it is also in on a log scale. So we have this distance 10 to 10 squared clearly is much smaller than 10 squared to 10 cubed distance. So anyway, so we said if you hold the austenite for a particular temperature, after a while, then it will become pearlite, if we're here. And of course, here is the beginning of my transformation. This line represents the start of my transformation. And this line represents the end of my transformation. So I'm 100% transformed here. Of course, the middle line would be 50-50. Now also, below 550, if you rapidly cool, you transform the austenite to bainite and hold. Rapidly cool to say 400 degrees and hold. For a period of time, the austenite will transform to bainite. So what were the differences between pearlite and bainite? Well, if you recall, the pearlite lamella was that eutectoid microstructure that we discussed earlier. So we had alternating layers of cementite and alpha ferrite, alternating layers or alternating lamella. Bainite was a little bit different. Bainite, we had a needle-like structure where you had cementite embedded in a ferrite matrix. You had cementite, which looked like fine needles embedded in a ferrite matrix. Then we said also if you rapidly quench the austenite all the way down to below around 200 degrees, close to 200 degrees, and in this ballpark here, then you have another microstructure formed. It is not a stable microstructure. It never really truly achieves equilibrium. So we don't show it on the diagram, or we show it on the diagram here, the isothermal diagram, isothermal transformation diagram. We show it as hash lines. And that non-equilibrium phase is represented, or microstructure is represented by the term martensite. And it looks similar to bainite in that you do have needle-like structures of cementite, again embedded in a ferrite matrix. Depending on what temperature you cool down to, if we cool down to, let's say, 130 degrees Celsius, then we would have 90% martensite and the remaining would still be austenite. If we cool down to, let's say, this one here, which is probably about 160 degrees perhaps, you'd have about 50% martensite and 50% austenite and so on. Now, very important to note that this transformation is diffusion-less. Okay, so martensite, the transformation from austenite to martensite is diffusion-less. Some other things we talked about last class. Recall that if we transformed austenite to pearlite when we're close to the eutectoid temperature, we would end up with coarse-grained pearlite. as opposed to when we're closer to that 550-degree line, we end up with fine-grained pearlite. Now, a couple things to note here. Why do you get coarse-grained pearlite? Well, at the higher temperature, you have a higher diffusion rate. So remember, you have alternating lamella of alpha ferrite and cementite, and they grow because of the diffusion of carbon. So you get more carbon diffusing, you get thicker layers, you get a coarser grain. Alternatively, or really similarly, at lower temperatures, if at higher temperatures you have faster diffusion, at lower temperatures you have slower diffusion. So here you're still going to end up with alternating layers because we're still talking about pearlite, but there's not enough. The diffusion is slow, so you get smaller or thinner layers of lamellae. Now, very important to also note that the transformation rate is not the same thing as diffusion rate. The transformation rate is, how quickly it achieves 100% transformation, within a specified time. So that's my transformation rate. So, for example, here it takes a long time for me to transform from austenite to pearlite. So the transformation rate is slower. The transformation rate is slower because it takes a longer time. Here it takes a very short time, so the transformation rate to transform from austenite to pearlite, so the transformation rate is faster. So you see that as temperature decreases, the transformation rate actually increases, which is sort of counterintuitive. And the reason for that is that in the austenite pearlite regime, the transformation is dominated by nucleation. The transformation is dominated by nucleation. So at lower temperatures, you actually get a quicker nucleation. You have more nucleation as opposed to grain growth. Remember, the transformation is always comprised of two phenomena, nucleation and grain growth. Grain growth is diffusion driven, but nucleation is based on temperature. So if at the higher temperatures you don't get as quick nucleation as at lower temperatures, right? So all that being said, we can see that the transformation rate would be slower at the higher temperature. Now if we come down here, it's a little bit different. With austenite bainite transformation, that transformation is more diffusion driven. So it's less driven by nucleation and more driven by grain growth. So which is driven by diffusion, right? So if we are at low temperatures, we have low rates of diffusion, which means that our grains are not going to grow, or lamellae are not going to grow very thick. Okay, or lamellae will not grow very thick. So really, you get thinner or fine-grained bainite at the low temperature here, and at this point here, you'd have coarse-grained bainite, fine-grained bainite, coarse-grained bainite here. Also, look at the transformation rate. It's a little bit different here, right? Because this one takes longer. So the transformation is slower at a lower temperature. The transformation is slower because this time span is longer here as opposed to here. And we're talking about the austenite bainite transformation. And we said, why is that? Well, the transformation rate, or the transformation, is driven by diffusion. So if diffusion is slow, right, then the transformation rate is also slow, right? Diffusion is fast, it's faster here because the temperature is a little higher, then the transformation rate is a little bit faster, okay? Alright, so we looked at, if we consider an alloy of eutectoid composition rapidly cooled from 727 to 165, we ended on this question. We said, well, what percent of austenite immediately transforms to martensite? So if I go back here and I'm rapidly cooling to about 165, so I'm above the eutectoid or at eutectoid here, and I just rapidly come down, 165 is about here. So I'm going to be at 50% martensite, 50% austenite. Right? We said that. Then we wanted to say, we did not do this one, so I'm going to do this one now. Cite two major differences between martensitic and pearlitic transformations. Okay, so recall we said with the martensitic transformation, that was diffusionless. We also said, well, we can also note that when you do a rapid quenching or rapid cooling, you're coming straight down. And that, as I come through here, and I go from M start to M at 90 degrees, let's say 90 degrees martensite, there's no time span, there's no time delays. Everything is, I'm still on that vertical line, as opposed to here, where there's a time span between the transition, right? This is just a rapid cooling. So the transition from austenite to martensite is practically instantaneous. So that's the other difference. So we can say here that for the pearlitic transformation, we do need to have diffusion, whereas for the martensitic transformation, that is diffusionless. There's not enough time for any diffusion to occur. And also, for as far as the transformation rate is concerned, the martensitic transformation is virtually instantaneous, while the pearlitic transformation is time dependent. Now, what if we add other elements? Normally, remember we have a phenomenon called solid solution strengthening, where we can add other elements to make your alloy stronger and sometimes more brittle, and then we have to do some manipulation to retain the ductility or the toughness. But anyway, this is what will happen to our isothermal transformation diagram, or this is an example of what might happen to your isothermal transformation diagram when you alloy. Essentially, in this case, we have an alloy steel, type 4340, and the difference here, you can see the weird shape of or the unusual shape of the IT diagram, and also there is a pro-eutectoid phase that now comes into play. So my austenite changes to ferrite, to that pro-eutectoid ferrite plus my pearlite, and then I have some intermediate phases here. We're not going to work with these IT diagrams. This is just here for demonstration purposes. Alright, so quick example. We can use our IT diagram to determine what microstructure we will have at a particular time temperature treatment, or with a particular time temperature treatment. Let's see, for example, what's happening here. So if we were to rapidly cool to 350 degrees and hold for 10,000 seconds, and this is still that iron carbon alloy at eutectoid composition. So if we rapidly cool to 350, I'm going to end up somewhere like here. Then I'm going to hold for 10,000 seconds. That's 10 to the 4th seconds. So I'm going to go all the way across, and then I quench it to room temperature after that. So 10 to the 4th here. So when I'm here, I'm still austenite, but then I hold it for a while, 10 to the 4th seconds, and I have transformed fully to bainite. Now then I quench it, I end up down here. But why did I not go to martensite? Well, remember, martensite is only formed from austenite. That's it. Martensite is only formed when you have austenite being quenched. Right? So it's going to be 100% bainite. Next one is a little bit more challenging. If I rapidly cool to 250 degrees and hold for 100 seconds and quench to room temperature. So let's see, I rapidly cool to 250, that's about here, and I hold for 100 seconds. Well, I haven't really gotten to this beginning of my change here. So if I'm still austenite. So if I go down, I rapidly quench now, my austenite becomes 100% martensite.